Today we're going to talk about similar figures. The past couple lessons have been primarily just really algebraic and working with how to set up a ratio, how to reduce a ratio, and then what we do when we have a proportion, a ratio equals a ratio. So they've been very algebraic in nature the past couple days, and those were some algebra skills that we really needed because they're going to be important to us in now applying to this geometric idea of. The idea of similar figures is the same idea of a scale drawing. So when an architect plans a building and they draw a blueprint, they don't actually draw it the size of the building. Right? So there's some sort of scale that they use to shrink down their drawing. But everything should have meaning still. It's not just a sketch, it still has meaning. Similar figures are the same shape in that sense, just like a house should look just like the blueprint. But the angles must be the same size. Okay, two requirements for similar. Angles must be the same size. Just like in a blueprint, the corners of the house are still 90-degree corners. Okay, just like they're actually going to be. That does not change in similar figures. The angles remain the same, and the sides are in some ratio with each other. So maybe they took 1 foot and turned it into 1 inch, or 1 foot turned it into 1 centimeter, or there's some sort of change that they made to rescale that figure. That is called the scale factor, okay? And it should be consistent for the entire figure so that each side of the house has that same ratio to the blueprint. Otherwise, things start to look kind of like funhouse mirrors. They get distorted, and it might actually look longer than it's going to end up being, or look wider than it's going to end up being. So that scale factor needs to be consistent for the entire similar figure. So two requirements: angles must be congruent, and sides must be in this ratio of a scale factor.
Is that why we couldn't prove triangles with angle, angle, angle?
That is why we could not prove triangles with angle, angle, angle. Correct. Two figures are similar. The symbol that we use is like the one that we put on top of the congruent symbol, just the little squiggle, just called a tilde. When you see just that, that means the figures are similar. So here we are told that these two figures are similar to each other, and then we're asked to find several things about them. The first thing we're asked to find is their scale factor. The scale factor is the ratio of the sides. So what we need to do is find two sides that we know the value of that match up with each other. So we call those corresponding sides. Two corresponding sides that we know the length of in each figure. So what would those be?
DC.
The DC. So that we could say then is 20 to 30. And we always want to reduce our ratios, so the scale factor is 2 to 3. The first figure is 2/3 as big as the second figure. Then we're asked to find the values of x, y, and z. To find those, we're going to use this scale factor and set up some proportions to solve. So we start with our scale factor of 2/3. Then if I'm solving for x, x is in the first figure, and the first figure in this problem is represented by the top. So x is going to go on the top. And what does x match with in the second figure? 21. So that will go on the bottom. Then we learned yesterday how to solve this. We cross multiply 3 times x. 2 times 21 is 42. And divide, and I get x equals 14. To solve for y, we're going to do exactly the same thing. Start with the same scale factor for this whole problem. That's our scale factor. Then y is in the second figure, and the second figure is represented by the bottom of this fraction. So y is going to go on the bottom, and it matches with what?
8.
8. So 8 will go on the top. Then we cross multiply like we learned yesterday. 2 times y. 3 times 8 is 24. Divide, so y equals 12. To solve for z, we begin with the same scale factor of 2/3. Z is in the second figure, so it will go on the bottom. And what does it match with? 10. Then we are going to cross multiply. 2 times Z, 3 times 10 is 30, divide, so Z is 15. Questions about how to solve for missing pieces? Yes.
Wait, what's the scale factor?
The scale factor is the ratio that all of the sides should share in common. The way we find it is by finding the pair of sides that we know the numbers for both of. So 20 and 30, and then set that up as a ratio and reduce it.
Is the scale factor always like the first one over the second one, or is it like the smallest?
Sometimes the problem will tell you, find the scale factor of, and then it'll give you a name to the other one, and then you want to make sure you do it in that order. Otherwise, it doesn't really matter.
Right.
So in this problem, it just said scale factor. We could have done it either way. We could have done 2/3 or 3/2. But if it says, like, find the scale factor of A, B, C, D to E, F, G, H, then you want to make sure you do it in that order. Other questions? Okay, the third one here says find the perimeters of the quadrilaterals. How do I find a perimeter? What is that?
Add up all the
sides together.
Add up all the outsides together. So we found X was 14. So in that first one, if I add up around, I get 20 and 10 is 30, 14 is 44, and 8 is 52. And for the other one, we found Y was 12 and Z was 15. So I add that up all around, let's see, 33, 78. Then it says find the ratio of their perimeters. First figure was 52, second figure was 78, so we set that up as a ratio and we want to reduce. What do those both reduce by? 2. If I reduce by 2, I get 26 over 39. Does that still reduce?
No.
By 13. 13 goes into both of them. Reduced by 13 gives me 2/3, which sounds a little familiar. That was our scale factor. The ratio of the perimeters will always be the same as the ratio of the sides. So in a problem, if you're asked for the ratio of the perimeters, you don't actually have to go through the trouble of finding the entire perimeters and then reducing. You can just do the scale factor. The perimeter ratio will be the same as the individual ratios. Questions? Okay, a few more questions. For these, we're going to use a few diagrams.
Whatever it says. Fish tail. Yeah. So I think Garby like that. And then he's like, whoa, save it, Libby.
All right, using these figures, we are going to look at whether or not some pairs of them are similar. We don't typically talk about 3 similar figures at a time. We typically just think about pairs of them. So A, B, C, D, and E, F, G, H. Are they similar to each other? And then why or why not?
Because the sides are.
Okay, the angles are all congruent. There are 2 characteristics for being similar. Angles must be congruent, so that's good. The angles match up. But the sides, if we look at the tops, they're in a ratio of 5 to 4. If we look at like the left and the right, they're in a ratio of 5 to 2. So an unlike ratio means that these two are not similar. What about A, B, C, D, and J, K, L, M? Angles are the same. Sides are all in a ratio of 5 to 3. So that works. What about A, B, C, D, and N, O, P, Q?
No.
Why not?
Because
Angles aren't the same. Two characteristics. The sides have to be in proportion, and they all are 5 to 6. But the angles must also be the same, and they are not.
So that bacon symbol is similar.
And yeah, similar with a slash through it. So.
Mr. Damon.
So it is not enough to just check and see if the angles are congruent, and it is not enough to just check and see if the sides are in proportion. You have to check both of those characteristics to determine if two figures are going to be similar to each other. If two polygons are similar, does that mean they are congruent?
No.
No. They could be different sizes. Their angles will be congruent, but their sides won't necessarily be. If two figures are congruent, does that mean they are similar?
Yes.
What would their scale factor be?
1.
1 to 1.
1 to 1. Okay? If two figures are congruent, then their angles are congruent and their sides are in a ratio. Their sides are exactly the same, so a ratio of 1 to 1. Are all regular pentagons similar?
No.
What does regular mean?
Their
concave.
are all the same.
Their angles are all the same?
So yes.
And
All the
Their
sides.
sides are
their
all
sides are all the same. So in a regular figure, we know all of the angles are the same, and we know all the sides are the same. So there's a little baby pentagon that follows that. If I draw a bigger pentagon that still follows that, to my best ability, will those be similar?
Yes.
Yeah, all the angles have to be the same because all pentagons have the same total, and if they're all dividing up equally, then all the angles are the same. And the sides, if they're all the same, should be in proportion with each other. The last thing I want to warn you of is that, like when we did congruent triangles, the order of the letters mattered because it established a relationship. In similar figures, the order of the letters matter. So if ABC is similar to DEF, that means that whatever angle A is should be the angle that equals angle D. Okay? And whatever angle B is should be the one that equals E. And whatever C is should be the one that equals F. So when we name similar figures, the names mean something. It tells us what is corresponding and what should be matching. So be careful with your names of similar figures. Questions? Your assignment is from 7.3.